2.4 Library of Functions, Piecewise Defined Functions. Okay, so there are several different types of functions, and we have to be able to graph all of these by hand in order for us to be able to graph a piecewise function. So let's start with the easiest, the constant function. So the constant function basically looks something like this. F of x equals b, where b is just a real number. So let's say we have a graph here. 1, 2, 3, -1, -2, and -3. If b equaled 2, so the equation would be f of x equals 2, it would look a little something like this. If it were -1, -2, and so on. The next one is the identity function. So identity function looks a little something like this. F of x equals x. So we've seen actually many identity functions already. Usually they have a number behind here though. So let's say x equaled 1. Your x is actually your slope. So here's a graph with a slope of 1. If say you had a number back here, like +1, then the whole graph would simply move up. So it will have a y-intercept of 1, because that's what this number back here means. The original identity function is only that. X being your slope. In other words, x equals m, which is slope. Now it's going to get a bit harder. The first one is the square function. The square function is also the graph of a parabola. So equation looks something like this. F of x equals x squared, thus calling it the square function. If you were to graph this, say you've got 1, 2, 3, 1, 2, and 3. Okay, so with a square function, since there is nothing in the back of here, we know that there's a point at the origin, like it was with the identity function. Then on either side, so if we go to x is 1, if we plug it in, 1 squared is 1. -1 squared, is also 1. 2 squared is 4. -2 squared is also 4. Link the points up. Not a very good job. But that's how you would graph a square function. The next one is called a cube function. Like the square function, the cube function is called that because f of x equals x cubed. So in this case, now the cube function is even harder than the square function, so you guys just have to remember all of this. Okay, so with a cube function, again, since there is nothing back here, that means that we have a point at the origin. And then, plug in again. If x equals 1, 1 cubed would be 1. If x equals -1, -1 cubed would be -1. And then 2 cubed would be 8, which would be somewhere over here. And the -2 cubed would be just off the page. So the function would look a little something like that. Next is the square root function. So we'll notice a pattern with the square root function or cube root function with the root functions. So basically the square root function looks a little something like this. F of x equals the square root of x. With a square root function, if, say, the regular square function looks like this, the square root function would look like this. So basically you're more or less taking this part of it and you're turning it this way so that now it's there. So you plot the points the same way, so I won't go over that, but just know that there is no portion down here for the square root function. This does not exist, only this top part. But just know that, alright, so say this is 1, the square root of 1 would be 1, that point right there. And then, let's say you went to 4, square root of 4 would be 2. Alright, so we just had square roots. Now we're going to talk about cube root. So the cube root function, the same way that the cube function looks like this, the cube root function looks a little something like this. So like the cube root function, but turned. As you can see, it's not a perfect turn. The two graphs don't quite curve the same way if you were to turn them. However, like with all the other functions, so the square root function looks like f of x equals, the cube root function, cube root of x. And that is why it's called the cube root function. Like all the other ones, you would say, so say we're here at 1, the cube root of 1 is 1, right here. Like all the other ones, you would simply plug in the points, and then since you already know what it kind of looks like, just remember this little pink graph, plug in the points, and draw out the rest. Alright, so moving away from the squares and the cubes, there's something called the reciprocal function. The reciprocal function is a little weirder. Like you might have deduced, reciprocal of x, 1 over x. The function. So let's plug in points. 1, if x were 1, 1 over 1 would be 1. So there's a point here at 1, 1. If x were negative 1, 1 over negative 1 would be negative 1. So there's a point here at negative 1, negative 1. Now if x were 2, 1 over 2 is 1/2. So there would be a point here at 2, 1/2. Same goes for if x is 1/2. There would be a point here up at 2. So you can kind of see that the function looks a little something like this. And so if we just fill in the ones for these. The reciprocal function is special in that the graph never touches the two axes. The two graphs just kind of curve away like that. Okay. Absolute value function. So the absolute value function looks a little something like this. F of x equals the absolute value of x. So we don't see the absolute value function very much, but it looks a little something like this. So since it's always going to be the positive value for x, in the first quadrant, it looks like a normal graph with a slope of 1. However, in the second quadrant, it looks like this graph mirrored over. And there's never going to be anything in the third or fourth quadrant. And so the absolute value function always looks like this, pretty much. Of course, there are exceptions. If there's something back here, the graph will move up or it'll move down, in which case there will be something in the third and fourth quadrant. But other than that, there's always a point at the origin, and it always has two straight lines, and it looks like a V. Okay, so finally, there's something called the greatest integer function. Now, the greatest integer function is kind of hard to understand. This is what it's written as. This part meaning that if, say, you had something and the interval was x is greater than or equal to 0 and less than or equal to 1, and that's your interval, this portion is telling you that f of x would be equal to 0 because that is the greatest number to which x is greater than or equal to. So say it was something like this. F of x would then be 1 because that is the greatest number that x is greater than or equal to. And since f of x equals a number, that means that the graph would look something like this. So say we were plotting this one right here. Since it starts at 1 and it's bubbled in, and we know that f of x equals 1, there's a solid point at 1, 1, and then there's a open point at 1 or at 2, 1. If we were to plot that part, then it would look something like this. So since f of x equals 0, because of that part, we would have a point right here at 0, 0, with an open hole here, and the line would be something like that. And so if you have all of your portions, it will look a little something like steps. Except, of course, you would have a closed point and an open point. So now let's try and put that all together. Say you have the function defined as f of x equals, so now piecewise functions are all written like this. Let's say you've got negative x plus 1 if this interval, and then 2 if x equals 1, and x squared if x is greater than 1. So this is what a typical piecewise function would actually look like. It has several portions within it, each portion telling you what the graph looks like for a certain interval of x. And that those intervals are specified on the right-hand side with the graph specified on the left-hand side. So let's look at this first portion. If x is between the interval -3 and 1, and it's -3 is less than or equal to x, which is less than 1. So we know that since it's less than or equal to at -3, that means that it must be a closed point. So we plug -3 into the formula. So it looks a little something like this. -3, negative of -3 plus 1, which is 4. So now we know that at -3 there's a closed point at -3, 4. It's right here. And then we would plug it in for -2. So negative of -2 is 2 plus 1 is 3. So here we are there. And then for -1, it's at 2. For 0, it's at 1. And for 1, there's an open dot at 0 because x is not less than or equal to 1, it is just less than 1. So then if we just connect these, we should form a straight line going from -3 to 1 with a closed dot at -3 and an open at 1. And then next part would be where it says x equals 1, f of x is 2. So when x is 1, that means that there's a point right up here at 1, 2. And this would be closed since it's x equals 1. So basically there's a coordinate that looks like this. Now the next part is x squared. And this is when x is greater than 1, so that means that there's an open dot at 1 squared. So 1 squared would be 1. So right there. 2 squared would be 4. And since we already learned what a parabola looked like, we don't have to graph too many more points. And so here you are. There is a piecewise function. Remember, with every piecewise function, you have to make sure that you put open points where it isn't inclusive and closed points where it is inclusive, and that the intervals match the f of x that it's given.